Hi, Prof. My name is Arif, and today I'll be going over the main points of my chosen research topic, edge intelligence and its application in autonomous vehicles. First, a brief introduction on edge intelligence. Traditional cloud-based intelligence suffers from latency and bandwidth limitations due to requiring centralized data processing. Edge intelligence addresses this by integrating AI capabilities at edge devices, allowing real-time localized decision-making. This is critical for time-sensitive applications like autonomous vehicles. This is the network outline of cloud intelligence. As you can see, all communication connects back to the central server in the cloud, and the AI model is only present within the cloud. However, for edge intelligence, the AI model has been transmitted across edge devices. Furthermore, most communication is done within edge devices and edge servers. Next, I'll continue with the benefits of edge intelligence. It achieves a significant reduction in latency by performing computations locally. Furthermore, it minimizes bandwidth consumption as data does not need to be sent to the cloud. Sensitive data can be processed locally, enhancing data privacy and security. And edge systems also continue functioning even with intermittent connectivity, and their modular nature supports scalable deployment as they can always fall back on the cloud. Furthermore, by using local data, personalized AI models can be created and maintained. Also, as edge devices offload their tasks to edge servers, they consume less power, giving them a longer battery life. There are four key components of edge intelligence. First, edge caching, which is about storing frequently accessed items closer to edge devices. Next, edge training, where lightweight AI models are trained directly on edge devices, which supports personalization and improves privacy. Edge inference is about using these models to support real-time tasks. And lastly, edge offloading is about dynamically distributing computing resources between edge devices and cloud servers to optimize performance and resource use. The key enablers of edge intelligence are model compression and federated learning techniques, which help to bring machine learning models to edge devices in the first place. The model compression techniques covered today include model pruning, quantization, and knowledge distillation. There are two types of model pruning. Unstructured or weight pruning involves removing weights in a neural network based on their importance, determined by certain heuristic functions, like magnitude-based pruning or Hessian-based pruning. This generally results in sparse models that require additional fine-tuning to regain optimal performance. Structure pruning, however, removes entire neurons, convolutional filters, or channels. These models are denser and better suited for deployment on edge device hardware. Quantization reduces the numerical precision of model weights, decreasing memory requirements of the model. The two common techniques are post-training quantization and quantization-aware training, the latter having incorporated quantization effects during training for higher accuracy. Knowledge distillation is a process where smaller, lightweight student models are trained to replicate the outputs of a larger, more complex teacher model. This allows high-performance models to be approximated efficiently at the edge. The student model is trained using the logics of the teacher model to improve its generalization. Federated learning is the collaborative training of machine learning models across multiple devices while ensuring that the raw data remains on local devices. Only model updates or gradients are shared and aggregated on a central server. This helps to enhance privacy and reduce communication overhead. For the application of edge intelligence, I chose autonomous vehicles, also known as AVs, as they require ultra-fast, high-confidence decision-making in real time. AVs have a wide array of sensors that produce vast amounts of data every second. Traditionally, such data will be sent to cloud servers, but that introduces unacceptable latency for safety-critical scenarios. Edge intelligence addresses this gap by enabling on-board or nearby edge nodes to handle data processing locally. This allows for AVs to accomplish essential tasks. The first is real-time object detection and decision-making, as AVs must detect pedestrians, vehicles, road signs, and other elements almost instantly. Edge AI models allow for real-time classification and action, such as applying brakes to avoid collisions. The next is lane detection and road condition analysis. AVs must stay centered within lanes while recognizing variations in road markings, lighting, and weather conditions. Edge models trained on local data help detect hazards like ice in colder climates or heavy rain in tropical regions. There are many applications that can benefit from edge intelligence, but there are still certain challenges that need to be solved, like hardware constraints on edge devices and deployment complexity due to system and data heterogeneity, which are issues caused by differences in system hardware and local data, respectively. In conclusion, edge intelligence is increasingly vital for the development of time sensitive, intelligent IoT applications. For AVs, it ensures faster, more responsive, and context aware decision making. However, there still exist challenges like hardware limitations and model deployment complexity that must be addressed through ongoing innovation efforts. As AI and edge technologies evolve, their convergence will continue to drive transformative solutions in both existing and emerging industries.